Hey everyone, I am Neelav Bhatiya and I gave my JEE in 2020 and I secured a rank of 1755. And today I am here to discuss the chapter Permutations and Combinations, which is chapter number 7. So before actually beginning this chapter and going through the exercises, it is very important for us to realize what this chapter is all about. So differing from the other chapter, you don't actually need to have as much grasp on theory as much as you need to have practice in this chapter. And the more number of questions that you solve, the more you'll be better able to attempt uh, the questions of this chapter, right? And most of these chapters, most of the questions from this chapter are uh, kind of derivative of real life scenarios that you might encounter. Supposedly, while you're tossing a coin or while you're playing a game, you might want to calculate the odds of something happening. Then this chapter will be equipping you with enough theory that you'll be able to do so. So it is a very fun chapter, and without wasting any more time, we could jump to the exercises. Yeah. So let us begin our discussion with exercise 7.1. As we move on with the exercises, I'll be sure to give you pointers here and there, which will help you kind of visualize how we arrived at the solution better, and will be really helpful in the coming time when you are solving the questions yourselves and arriving at the solutions, right? So the first question that we have for the day is question number 1 in exercise 7.1. We're discussing question number 1. So question number 1 says, how many three-digit number can be formed from the digits 1, 2, 3, 4, and 5, assuming that first part, repetition of the digits is allowed. So we need to form a number which is 3 digits long, and we are allowed to use 1, 2, 3, 4, and 5. Correct. These are the digits that we have to use to form this number. So how many ways can we fill in the first digit of the number? As we have 5 choices to use, this can be filled up in 5 ways. Similarly, the second digit of the number can also be filled up using 5 ways, because we can use either of these digits again, right? Because the repetition is allowed in the first case. And similarly, in the third digit, we can also use all 5 digits to fill it. So when you do that, the answer that we get is 5 into 5 into 5, which is nothing but 5 cube, which is nothing but 125. So 125 numbers can be made which are 3 digits long using 1, 2, 3, 4, and 5 if a repetition is permitted, right? Second case, let us suppose that repetition is not allowed. Then our discussion becomes a little interesting, right? Because the first digit can obviously be filled using 5 ways. We can use either of 1, 2, 3, or 5. I mean 1, 2, 3, or 4, or 5, right? Any of them can be used. But the second digit, now let us suppose that we used 4, right, to fill the first digit. Let us suppose the first digit, the number that we chose was 4. Now we cannot use 4 because repetition is not allowed. The choices that we are left with is 1, 2, 3, and 5, which are 4. Correct. Moving on, let us suppose that we use 2. Now the number of choices that we have is 3, because we can only fill the last digit with 1, 3, or 5. So eliminating one more, we get 3. Correct. Now calculating this, the final answer that we arrive at is 60. I hope this was clear. This was very trivial. So whenever you are faced with such questions, right, be sure to have the condition very specific in your mind. If the repetition is allowed, think along those lines. The numbers that you are filling the digits that you are filling the number with might be repetitive as well. So keep those conditions in your mind and you'll be good to go. These are sort of very trivial questions that could be asked in this chapter, but we'll begin our discussion with easier questions, and then as the chapter proceeds on, we'll jump on to some interesting questions as well. Right. So this was the first question. Question number 2. How many 3-digit numbers can be formed using the digits 1, 2, 3, 4, 5, and 6 if the digits can be repeated? Okay, so this is interesting. It is asked that we need to form a 3-digit number again as the same as the first question, but the condition that is being given to us is that the number should be even. Now, what do I mean by that? For any number to be even, right, the trailing digit has to be even. Only then it is divisible by 2, and only then is it even, right? So that is one of the conditions that is imposed upon us. No condition has been imposed upon the digit at hundreds place and tens place. So we can fill them in 6 ways, correct? Because we have 1, 2, 3, 4, 5, and 6, which you are going to use to make up the number. So 6 into 6, because there is no boundary on us using any digit in the hundreds and the tens place. So first of all, I'm going to just go on and write that. But as we have been specified that the number is even, at ones place, we cannot use any of the odd digits. Correct. So the choices that we are left with are 2, 4, and 6. So the number of ways with which we can fill the last digit is 3. If you go on and calculate this is nothing but 36 into 3, which is nothing but 108 numbers. Correct. This was the second question as well. Now, before moving on, as I said, please carefully take a look at the condition that has been imposed in the question. We have been said that we can only use even numbers, right, to form the entire the number can only be even. So that is the separating part between the first question and the second question. These are minute details which might lead you to find the wrong answer. So keep these things in mind while you're reading the question, right? Make sure you read the right thing and take a minute before actually moving on to the solution. That was question number 2. Moving on. We are on to the question number 3. How many 4-letter code can be formed using the first 10 letters of the English alphabet if no letter can be repeated? Correct. So that is what we are going to see now. So the code that we are forming is 4 letters long. So whenever you approach such questions, right, make sure to make these blanks as I'm doing on the screen right now. This will help you to visualize the solution better and come and arrive at the solution faster, right? Because you have filled up this digit or you have filled up this place in the answer, and then you'll be able to think along other lines, right? So we can use the first 10 letters of the alphabet, and repetition is not allowed. So the number of ways that we can fill up the first letter is 10. Correct. The number of ways we can fill up the second letter is not 10 now, it is 9, because repetition is not allowed and we've already consumed one letter. Think how we approach the first question and you'll be better able to visualize how we arrived at this, right? So 9 here, similarly 8 here, and now we are only left with 7, so 7 here. When you go on and multiply this, the answer that you're finally going to arrive it as 5040. This is your final answer. So 5040 codes can be generated, which are 4 letters long from the first 10 letters of the alphabet, where repetition is not allowed. Correct. Moving on, question number 4. So question number 4, we have been asked that how many 5-digit telephone numbers can be constructed using the digits 0 to 9 if each number starts with 67 and no digit appears more than once. Okay, so this is interesting now. So we have been asked to generate 5 numbers long telephone number, but the first 2 digits, right, they have already been specified to us that the number that we are going to generate always starts with 67. So the places that we have left to fill are 3 that are remaining right now. Correct. And we have already consumed 2 digits. So 0 to 9 consist of 10 digits, 10 distinct digits, right? Off of these 10 distinct digits, 6 and 7 have already been used. So 10 minus 2, the number of choices that we are left with is 8, correct? So this can be filled up. It's filled up using one ways. This is filled up using one ways. And now that 2 digits have been consumed, we can use the remaining 8 digits to fill up this place. So 8 here. Now one more has been consumed, so 7 digits remaining. And one more has been consumed, so 6 digits remaining, correct? When we multiply this, the answer that we arrive at is 336 numbers, correct? So this is your final answer, and these are the number of phone numbers that you can generate, keeping in mind that they should start with 6 and 7, and that all the digits should be distinct, correct? Moving on to the fifth question. Question number 5. A coin is tossed 3 times and the outcomes are recorded. How many possible outcomes are there? So up until now, we have only talked about digits and letters and things that can be enumerated in a sequence, right? But consider tossing a coin as the same thing. Rather than places, right? The blanks in this case will now represent the outcome of each toss, right? And think about when you are tossing a coin, there are only 2 possible outcomes, right? Either you can get a heads or you can get a tails. So in each of the 3 tosses, you have 2 choices to fill up the blank here, correct? Because in each outcome, it could either be heads or it could either be tails. So calculating that, you get 2 into 2 into 2, which is nothing but 2 power 3, is nothing but 8. So the number of outcomes that are possible is 8, correct? This is a fairly trivial questions that you don't have to apply much of your logical thinking here. You just have to do what has been stated in the question, quite straightforward, and you'll arrive at the answer very easily. Question number 6. Given 5 flags of different colors, how many different signals can be generated if each signal requires the use of 2 flags, one below the other? So let us suppose that this is your sample space, or this is your space wherein you have to generate your signal, right? So it has been divided up into 2 places. This is filled up using flag 1, and this has been filled up using flag 2, correct? Now it has already been stated to you that you have 5 flags that you could use. So the first part of the signal can be made up using 5 choices. But as you have already consumed one of the flags in this choice, right? In the second part, you are left with only 4 flags, right? So this can be filled up using 4 ways. So the number of distinct signals that could be generated is 5 into 4 is nothing but 20 signals, correct? And this is your answer. So this was all from exercise 7.1, a fairly trivial and straightforward exercise. If you ask me, you just have to do what has been asked of you, and as you fill up places, your answer will be generated in front of you. So you don't have to apply much logic here or much thinking in this exercise to say so. But this forms a basis of how you're going to approach questions in the later exercise, right? So I'd recommend that you try this by yourself, and even if this is fairly straightforward, you just put this to a logical end and try all the questions in this exercise, correct? Now that we have completed exercise 7.1, we are going to be moving on to exercise 7.2. Question number 1. Now, as I'm moving on, you might be seeing these notations and how permutations and combinations have their various formulas and things as such. I'd recommend that you try these things for yourself as well. So as and when you're solving the questions, right, you don't feel as if you're stuck. Just go through the sample exercises that have been solved for you as well, and That is how you'll be good to go. Correct. Question number 1, exercise 7.2. First part. So first part is fairly straightforward. We have been asked to evaluate 8 factorial. And as you know, this factorial notation is nothing but numbers multiplied in a series from n, where n represents the factorial that you're calculating, to the first natural number, that is 1, right? So 8 factorial is nothing but 8 into 7 into 6 into 5 into 4 up until 3 into 2 into 1. Correct. So that is what is 8 factorial, can be denoted as this symbol right here. And if you are to go on and actually solve this, you would get your answer to be 40320. Correct. And I would kind of recommend you guys to actually calculate this not using a calculator, but doing all those tedious multiplications yourself, because permutation and combination, a lot of it is also calculating things. And the as much as you do that, right, you will have more proficiency and efficiency in getting to your answers. So I'd recommend that you do these tedious calculations all by yourself and not rely on calculators while you're solving these exercises, right? That is one of my tips for you guys. Moving on to the second part of the question. Second part is 4 factorial minus 3 factorial, and you have to evaluate this. So when you are approaching such questions, right, or for that matter, when you're approaching any of the questions that involves factorials or permutations or combinations, try to figure out if there is something that you could take out of all the operands that you have in the question, right? So in this question, I have 4 factorial and 3 factorial, but I know for a fact that 4 factorial could be expressed as 4 into 3 factorial, right? I've done nothing, but I've just opened up 4 factorial into its constituents, and what I've got is 4 into 3 factorial. Here I have 3 factorial. Correct. Now in both these operands, I can take out 3 factorial common. So that is what I'm going to do. I'm going to take out 3 factorial common. What I'm left with in this term is 4, and what I'm left with in this term is nothing but 1. So I have 3 factorial into 3, and that is nothing but 6 into 3. That is nothing but 18. There you have it, folks. It is evaluated. And this practice, right, it's going to make your life much easier, rather than first calculating 4 factorial and then calculating 3 factorial and uh, taking out the difference. You could just do this, take 3 factorial out common from both the operands, and your life will be much simpler for that. Moving on to the second question. In the second question, it has been asked whether 3 factorial plus 4 factorial is equal to 7 factorial or not. So this might seem very trivial to you guys, and it actually is. When we are doing such questions, right, it is very imperative for us to kind of remember how to approach this question, right? So you can, whenever you are trying to prove something right or something wrong, you start this question by first solving the LHS and then solving the RHS, and that is how you're going to show your work. As it is, we know that factorials are not additive in nature. So 3 factorial plus 4 factorial is not 7 factorial. But just to kind of show your work, right, what you're going to do is you're going to solve the LHS, solve the RHS, and then you're going to prove that as these terms are not equal, we can be sure of the fact that 3 factorial plus 4 factorial is not equal to 7 factorial. Correct. So I'll do that for you guys. The LHS is 3 factorial plus 4 factorial. Expanding that, what I'm left with is 3 into 2 into 1 plus 4 into 3 into 2 into 1. 3 into 2 into 1 is nothing but 6, plus 4 into 3 into 2 into 1 is 24. And finally, the LHS comes out to be 30. Correct. Solving the RHS, 7 factorial is nothing but 7 into 6 into 5 into 4 into 3 into 2 into 1. Correct. Solving this, what I'm left with is 5040, which is equal to my RHS term. As LHS and RHS are not equal, I can say for a fact that 3 factorial but plus 4 factorial is not 7 factorial. Correct. Moving on. Question number 3. We have to compute this 8 factorial upon 6 factorial into 2 factorial. Correct. So if you had to approach this question in the brute force manner, what you would do is first you would calculate what is 8 factorial, which would come out to be some big number, and we have calculated that in the first part of this exercise itself. And then you would calculate 6 factorial, which would again be a big number, multiply that by 2 factorial and perform the division. But that is a very non-efficient way of doing things. Rather than doing that, let us simplify the term first, and then we can carry out our calculations, right? So 8 factorial could be written as 8 into 7 into 6 factorial. Correct. I've done nothing but I've expanded 8 factorial into its constituents, and similarly I'll keep 6 factorial as is, 2 factorial as is, and as you can see, I'm able to cancel out 6 factorial because it is the common term in both the numerator and denominator. All I'm left with is 8 into 7 divided by 2 factorial, and 2 factorial is nothing but 2, so I'll straight up cancel 2 factorial with 4 and with 8, and 4 will be remaining here, and what I'm left with is 4 into 7 is equal to 28. As you guys can see, rather than doing all the calculations, we were just able to simply figure out what the answer will be when we cancel out 6 factorial from the numerator and denominator. And that is how you are going to efficiently approach such questions, right? Now, moving on to the fourth question. This is an interesting one. Now, we have question number 4 with us, which says 1 upon 6 factorial plus 1 upon 7 factorial is equal to x upon 8 factorial. Correct. So rather than actually calculating out these factorials, what I'm going to do is I'm going to take out things common, and we'll be able to better visualize how we are able to efficiently solve this question, right? So first, let's simplify the LHS. Because 7 is the term that is differing here, I can write the first term as 7 upon 7 factorial plus 1 upon 7 factorial equal to x upon 8 factorial. Correct. I've done nothing but I've multiplied the numerator and denominator of this term by 7, right? What I'm left with now is 8 upon 7 factorial is equal to x upon 8 factorial. This can be cancelled out. 8 is remaining here. What I'm left with is x upon 8 equal to 8. Cross multiplying on that side, what I'm left with is x equal to 64. So taking out factorials common and taking out and then cancelling them out kind of makes our job a lot easier, and we are able to calculate these things at a much faster pace, right? So this is something that you guys need to keep in mind when you are approaching permutation and combination questions, and that is how you will be able to better visualize this and arrive at these answers faster, right? So that was all from this question. We have question number 5. Question number 5 says that we need to evaluate n factorial upon n minus r factorial when. So let me just write these things. Correct. The first part says that n equal to 6. Sorry. N equal to 6. R equals to 2. Correct. This is the first part of the question, and this is also fairly straightforward of you to solve. This just involves calculation on your part, but I am going to solve it for you regardless. So first part, just plug in the values of n equal to 6 and r equal to 2 in the above equation, what you're left with is 6 factorial upon 6 minus 2 is 4, and 4 factorial down here. 6 factorial could then be broken up into substituent components, which would result into something like this. And as you can see, now we can take 4 factorial out common from the numerator and denominator. Cancelling that out, what you're left with is 6 into 5, which is nothing but 30. That is the answer for the first part. Moving on to the second part. Second part, we have n equals to 9, r equals to 5. We have 9 factorial upon 9 minus 5 factorial, correct, which is nothing but 9 factorial upon 4 factorial. Taking out things common from here, I will have 9 into 8 into 7 into 6 into 5 into 4 factorial upon 4 factorial, cancelling these things out. And finally, I'll be able to arrive at the answer by multiplying 9 into 8 into 7 into 6 into 5. And if you were to go on and do that, the answer that you will get is 15120. Correct. That is your final answer. And we have 2 or 3 more exercises, I presume, coming on. And we will go ahead and discuss exercise 7.3 at the next lecture when we are going to start that. Up until then, I would advise you all to revise all these practice questions that we just saw between exercise 7.2 and exercise 7.3. These are going to form the crux of the chapter that you're going to solve. So be sure to do that. And yeah, that will be all from my side for this class. And be sure to practice, because this chapter involves not more of theory but practice on your part. And the more you're going to practice, the more you're going to be better able to solve the questions, right? So revise all this theory before actually attempting 7.3, and we are going to discuss exercise 7.3 and all the other exercises in the next class. Okay, thank you. So moving on, guys, now we'll be able to solve exercise 7.3 as we have discussed exercise 7.1 and 7.2. So this exercise is going to be slightly tricky, and you will be required to be well versed with the formula of how permutations and combinations formula actually work, right? So if you have not done that, I would request you guys to first go on with the theory and then come back to the solution session if you're not able to solve a particular question in this exercise, and you'll be better equipped to understand how we have arrived at the solution if you do that, right? So moving on, how many so question number 1 we are going to discuss how many three-digit number can be formed using the digits 1 to 9 if no digit is repeated, correct? So we have 9 digits to choose from, and we know that no digit can be repeated here. So earlier, what we used to do to approach such question is we used to make these 3 places, and we used to fill these places with appropriate choices, and we used to arrive at the answer. But now, having studied permutations, we have a more efficient way of doing these things. So rather than filling in these places, the question straight up asks us to permute 3 digits from 9 digits and make them fill up places. So our answer would be nothing but 9p3, correct? Because you are using 9 digits and we have 3 places to fill. So we'll just write 9p3 because we want to permute these digits in any combination that we want, and we need to select them and fill them in a random order. So 9, so that would be 9 factorial upon 9 minus 3 factorial, because 9 n p r is nothing but n factorial upon n minus r factorial. I've done nothing but I've just expressed that in the actual terms of 9p3, And when you go on to solve this, you'll realize 9 factorial is nothing but 9 into 8 into 7 into 6 factorial upon 6 factorial. Cancel 6 factorial from numerator and denominator. And when you will go on to solve this, the answer that you are going to arrive it as 504. So 504, 3-digit numbers are possible when you have 9 digits to permute from and 3 places to fill, right? So that is your final answer. Moving on to the second question. In the second question, it has been asked of us that we need to make 4-digit numbers with no digit that can be repeated. And we have been given the choice of any digit to choose from. We have 10 digits to choose from, but we have to make a 4-digit number out of them, right? So this is interesting. First mistake that students tend to make in this question is that they think that, okay, we have to make a 4-digit number. We have 10 digits. Repetition is not allowed. So answer is straight up 10p4. But this is wrong. And the reason that this is wrong is this consists of cases where your number begins with 0. And a number beginning with 0 is not actually a 4-digit number, it's just a 3-digit number. So when you arrive at the answer using this trick, the solution is wrong. Correct? So first you need to take that into consideration, that while filling up the first number, right? First digit, you don't actually have 10 choices. You only have 9 choices because 0 can't be used, right? But now that you have used 0 up, or you have not used 0 up, subsequently 0 can be used, right? So let us suppose that you have 0 1 2 3 4 5 6 7 8 9, correct? So 0 for the first case can't be used. So let us suppose that you use 4, or early, let us count the number of choices you have when 0 can't be used. 1 2 3 4 5 6 7 8 9. So you have 9 choices when 0 can't be used. But after filling up the first digit, let's suppose that you use 2, 0 can now be used. So now again 1 2 3 4 5 6 7 8 9, you have again 9 choices remaining with you. So the second digit can also be filled up using 9 ways. Let us suppose that you now use 1. Now the number of choices that you are left with is 0 or 1 2 3 4 5 6 7 8. So 8 choices for the third digit and 7 choices for the last digit, and therefore the final answer that you get is 9 into 9 into 8 into 7. Calculate this. 4 5 3 6 numbers are possible. Correct. So that is the crux of finding out how many numbers can be 4-digit numbers can be made when repetition is not allowed, and that is how it is done, right? Now the fourth, we have on to the third question. I'm sorry, third question. Just a moment. Yeah, question number 3. How many 3-digit even numbers can be made using the digits 1 2 3 4 6 and 7 if no digit can be repeated? Correct. So let us just make all these places and let us write the digits that we have at our disposal. Correct. So the first condition that has been specified to us is that the number is even, right? What does that tell us? That tells us that the digit at units place can either be 2, 4 or 6. So the number of ways that you can fill up the last digit is 3. Does that make sense? This is because we can only use even numbers or even digits to fill up the last digit. So I have 3 choices. Out of these 3 choices, I've selected one. Let's suppose that I've selected 2 to do that, right? I had 3 choices. Now let us see how many choices you have to fill up the tens place and the hundreds place, right? For the hundreds place, I can now use any digit, provided that I am not using the same digit, because repetition in this case is not allowed. So for the tens place, I now have 1, 2, 3, 4, and 5. So 5 choices right here. And for the hundreds place, I have used up, let's say, 2 digits. I have no any other restrictions I don't have. So I have 4 more choices to fill the hundreds place by. That will be 4. And finally, the answer that we arrive at is 4 into 5 into 3. That is nothing but 60. So 63 digit numbers are possible using 1, 2, 3, 4, 6, and 7 when the numbers are even and the digit are not repeated. Correct? Question number 4. Find the number of 4-digit numbers that can be formed using the digits 1, 2, 3, 4, and 5. If no digit is repeated, how many of these will be even? Correct. So this question can be divided up into 2 parts. Correct. The first part asks us that how many 4-digit numbers are possible straight up. We have to do nothing but we have to permute 4 digits out of the 5 digits that has been given to us, and we will arrive at our answer. So the number of places that we have to fill up are 1, 2, 3, and 4. Out of these 4 places, we have 5 digits to choose from, and so the answer would be nothing but straight up 5p4, which could be written as nothing but 5 factorial upon 4 factorial. Sorry, 5 factorial upon 5 minus 4 whole factorial. There is nothing but 5 factorial upon 1 factorial, which is nothing but 120. So 120 distinct numbers can be made up using 5 digits when you have to fill in 4 places, right? Off of this 120 numbers, how many of these numbers are going to be even? So the tedious way of doing things would be to make another question wherein only even numbers were possible, and then you would go on to fill the units digit first by 2 and 4, and then you would go on to solve the answer. But rather than doing that, let us think in terms of probability. So the last digit can be filled up using 2 or 4, and the total number of choices that we have is 1, 2, 3, 4, and 5. 2 and 4 are the choices which, when used to fill up the units place, would result in an even number, right? Like without that, we have no other restriction to choose the digits that go on in any place, right? So we have total number of 5 choices, 5 distinct choices that could fill up the units place. Off of these 5 choices, 2 choices would result in even numbers. So the probability that the number that we generate is even is nothing but 2 upon 5, is nothing but 0.4. Correct. Now that you have obtained this fraction, you do nothing but you multiply 0.4 by the total number of generated numbers. So even numbers would then be 0.4 into 120, and that is nothing but 48. You see how we arrive at the answer? We do not think in terms of generating an even number from scratch. We think in terms of the probability of the number that we have generated being even, and that is how we arrive at a solution faster. Correct? So that is another way of doing this question. You could always approach this question in the traditional way and generate the even numbers from the available digits at your disposal, and you'll arrive at the same answer. The number of possible even numbers is also 48, but this is a faster way of doing things, right? Just think in terms of probability and you will arrive at the solution faster. Question number 5. From a committee of 8 persons, in how many ways can we choose a chairman and vice chairman, assuming one person cannot hold more than one position? Correct. So we have a committee of 8 people. And off of this 8 people's committee, we have to choose a chairman and a vice chairman. So just at a glance of this question might seem that this is not related to permutations and combinations as such, and you have to think along different lines. But try to visualize this question in terms of letters and digits and how it is used in filling up places, right? So think of chairman and vice chairman as not them being two distinct positions, but them being just places that you have to fill, and the choices that you have are 8 people in the committee, right? So the number of ways that you could fill up the chair position would be 8, and as people cannot have more than one position, the number of ways that you could fill up the vice chair position is now 7, deducting the one person that you used in filling up the chair position. So the answer would be nothing but 8 into 7, which is 56. So 56 number of ways are there with which you can fill up the vice chair and chair position. Correct. Moving on. We need to solve for, I'm sorry, we need to solve for n in question number 6 when n minus 1 p3 upon n p4 is given to us as 1 over 9. Correct. So this actually is not a permutation combination question. It is a question of algebra, and all you need to do is solve the equations in terms of the formulas that you have remembered up until now, and you'll be able to find out the answer pretty straightforward. Right. I'm going to solve this for you. So n minus 1 p3 would be nothing but n minus 1 whole factorial upon n minus 4 factorial. Correct, because n minus 1 minus 3 would be n minus 4, and subsequently the denominator would be n factorial upon n minus 4 factorial. This and this gets cancelled out. I have 1 over 9. Solving this further, removing this, I'm just removing this, solving this ahead. I have n minus 1 factorial upon n factorial equal to 1 over 9. This gets cancelled. What is left with is n. So 1 over n equals 1 over 9. Cross multiplying, we have n equal to 9. Right, and that is our answer. It's a very straightforward question. You just had to take out factorials common, expand the NPR formula and take out the factorials common, and you'll be able to find out the answer. Pretty straightforward. Moving on. Now we have question number 7. Correct. In question number 7, we have to solve for 2 parts, right? First part is we have to find, in both the parts you have to find r. For the first part, the question that has been given to us is 5p r equals to 6p r minus 1, and we need to solve this for r. So this is also an algebraic question. This is not a permutation combination question as such, but yeah, we are going to solve this using nothing but algebra. And first we'll expand the NPR formula, and then we'll solve for r, which will result in an algebraic equation, and we'll be able to solve that, right? So I'll just expand. So 5pr is nothing but 5 upon 5 factorial upon 5 minus r factorial into is equal to 2 into 6 factorial upon, again, 6 minus r plus 1 factorial. Correct. So this could be cancelled. This becomes just 6, and subsequently what you are left with is 2 into 6 equals 7 minus r factorial upon 5 minus r factorial equal to 12. Correct. Just remember this. So if we need to divide this by 5 minus r factorial, what we can do is we can expand this, right? So this will become 7 minus r into 6 minus r into 5 minus r factorial upon 5 minus r factorial is equal to 12. Cancelling 5 minus r factorial out from the numerator and denominator, the equation that we are left with is 7 minus r into 6 minus r equal to 12. Correct. All that is required is now to solve this. I'm going to rub certain things and we're going to solve this equation, right? So 7 minus r into 6 minus r would be nothing but 42 minus 6 plus 7 is equal to 13. So minus 13r plus r square equal to 12. Correct. So 12 goes in this direction. So what you're left with is r square minus 13r plus 30 equals to 0. Correct. Taking out factors common, what you are left with is r minus 10 into r minus 3, because 10 plus 3 equal to 13, 10 into 3 equal to 30, and that is how you solve this question. So we have r equals to 10 or r equals to 3, but we are going to reject one answer from here because we know that we cannot have a number. We can sorry, we are going to reject 10 from the answer because we cannot have r being greater than the permutation. So we have 5pr which is given to us in the question. R cannot assume a value that is greater than equal to, that is greater than 5, right? So r equal to 10 is rejected. R equal to 3 is our final answer. Correct. Moving on. Just a moment. We were solving question number 7 only, so need to change that. But we are on to the second part. Second part also an algebraic question, and nothing but we have to write the answer here and there. So we have 5pr equals 6pr minus 1, and we have to do nothing but solve this. So 5pr is 5 factorial upon 5 minus r factorial is equal to 6 factorial upon 6 plus 1 minus 6 minus 1 plus r factorial. Cancelling this out, we have 6, and we have 7 minus r into 6 minus r into 5 minus r whole factorial upon 5 minus r factorial is equal to 6. Cancelling this out, this has been the same procedure that we followed in the first question as well, and we are going to do nothing but we are going to solve this as well. So I'm going to rub this part and solve this equation as we did in the first part as well. The equation on the RHS is going to be the same. It's going to be 42 minus 13r plus r square equal to 6, and you take 6 out on this side, you get r square minus 13r plus 36 equals to 0. So 9 into 4 equal to 36 and 9 plus 4 equal to 13. That's how you actually factorize this equations. You just take the factors into consideration in your head, and it will be very easy if you do that once. You don't even have to write anything. So 9 and 4 are my factors. Similarly, as we did in the first part, we will reject r equals to 9, because in 5p r cannot be greater than 5. This cannot happen. So 9 is rejected. R equal to 4 is selected, and that is our final answer. Okay. And so moving on further in this exercise. We have, sorry, the heading. Yeah, so we are on exercise 7.3, question number 8. How many words with or without meaning can be formed using all the letters of the word equation, using each letter exactly once? So we have E, Q, U, A, T, I, O, N. So all the letters, which are 8 to be precise, are distinct in the word equation, and we need to use all these letters exactly once to enumerate all the all the different words that could be possible and could be generated from this particular word, right? So we have 8 letters, and because none of them are repeating, right, all that is required is to permute 8 letters off of 8 letters, that is 8p8. That will be our final answer. So 8p8 is nothing but 8 factorial upon 8 minus 8 whole factorial. 0 factorial is just 1, so the answer is nothing but 8 factorial. If you were to solve this, you would realize that 8 factorial is nothing but 4340320. Correct. So that is the number of distinct words that are possible from the word equation. Correct. Moving on to question number 9. So the question number 9, 10, and 11 have many subparts as such, and these are the questions that are actually going to be tricky for you all. So pay extra attention when you are going to solve this question. And yeah, that is one advice that I would like to give you all. How many words with or without meaning can be made from the letters of the word Monday, assuming that no letter is repeated, if 4 letters are used at a time? Okay, so the word that we are using is Monday. In Monday, for the first case, we are going to be using only 4 letters. Off of the 6 letters that we have, we are only going to be using 4 letters. So first we select any 4 letters at random, and then we permute them. That is nothing but 6p4. That is nothing but 6 factorial upon 6 minus 4 factorial. And when you're going to solve this, realize that is nothing but 6 into 5 into 4 into 3 into 2 factorial upon 2 factorial, and that gets cancelled. And when you solve this, it's 6 into 5 is 30, into 4 is 120, into 3 is 360. So 360 distinct words are possible when you use 4 letters of the word Monday and make words out of those, right? Moving on to the second part. Second part says that we have to use all the letters. So as we did in question number 8, we are going to use all the letters, and there is no restriction as such upon us. So that will be nothing but, in the second part, we are just going to do 6p6, permitting all the letters all at once, and that is nothing but 6 factorial. As we saw that 6 minus 6 is 0 factorial, and that does not constitute any number as such. It constitutes 1, but it does not constitute a divisor. So that is nothing but 6 factorial, and 6 factorial is nothing but 720. So 720 distinct words are possible when you use this, right? So that is all from our end. Now moving on to the third part. This is the most interesting part of the question. And yeah, so we have 6 places to fill, right? But the condition that has been imposed upon us right now is that the first letter of the word is always going to be a vowel. That is the condition that has been imposed upon us. So as we know that we have O and A as vowels in our word, sorry. So the number of ways that we can fill up the first letter is 2, correct? And now the number of places that we have remaining are 5. So then we have to permute 5 places using 5 digits, 5 letters, sorry. So you have 5 into 4 into 3 into 2 into 1. This is nothing but representation of permitting 5 letters of 5 choices, right? So the answer that you're going to arrive it as 5b5, and that is nothing but 2 into 5 factorial, that is nothing but 2 into 120. So your final answer is 240, correct? That is how you're going to solve this question. So that is how you're going to actually solve question number 9. Now moving on to question number 10. So question number 10 is also an interesting question. So we have been asked that if in how many of the distinct permutations of the letters in Mississippi do the 4 I's not come together. So the way that we approach such questions is, right, we first calculate all the permutations, all the distinct permutations of the word Mississippi that are possible, and off of this uh, permutation, we subtract all those permutations where all the 4 I's are together, correct? And that is how we're going to solve this question. So before actually carrying on with the calculation, we need to have a tabular arrangement wherein we can see the number of distinct letters and how many times do they constitute them, right? So we have M in Mississippi, which is there just once. We have I, which is there 4 times, as you can see. We have S, which is also there 4 times. And we have P, which is 2 times, right? So this is the distribution of letters in the word Mississippi, correct? Now, how many distinct permutations of this word are possible, right? So whenever you are calculating permutations of a word wherein the letters are repeating, all you do is you permute all the letters as if they are distinct, because the number of letters in Mississippi are 11. So I'll just write 11 factorial and divide that sorry, divide that by the number of uh, repeating letters, right? So I have I 4 times, so I'll divide that by 4 factorial. I have S 4 times, so 4 factorial again. P 2 times, so 2 factorial again, and M 1 times, so 1 factorial again. And that will be the first part. Let me constitute that by P, right? So P is the total number of permutations that are possible. And when you were to go on and calculate the exact value of this term, the answer that you are going to arrive at is 34650, and that is your P. So this is the total number of permutations that are possible, right? we need to calculate the permutations where all the four i's are not together. So to arrive at the answer, I'll first of all make sure that I write P here as, so I don't forget, P 34650. Now I'm going to erase, and how I'm going to calculate the answer is, now I'm going to place all the four i's into one bucket and consider them as a single letter, right? When I find out the permutation in that manner, I'm going to subtract that from the permutation, all the permutations that I have, and that is how I'm going to arrive at the answer, right? So I'm going to treat all i's, all four i's as a single letter, right? Let's suppose some letter X, and then I'm going to permute the combination. So consider all i's as just one letter. So the total number of letters that you now have are 1 plus 1, 2 plus 4, 6 plus 2, 8. Correct. So considering all four i's together and as a single letter, the permutations that are possible denoted by Q will be 8 factorial, the total number of letters now, divided by 4 factorial because S are repeating, into 2 factorial, into 1 factorial, into 1 factorial. Correct. Because I've treated I as a single letter and M as a single letter, so I get Q as this, and when I calculate that, Q comes out to be 840. Correct. So I have P, I have Q. All that is remaining from my side is to calculate the difference, and that is going to be my final answer. Right. So answer is nothing but P minus Q, where P is total permutation and Q is all the permutations where all four i's are together. Correct. So I have 34650 and Q came out to be about 840. And subtracting that, the final answer that I get is 33810. Correct. That is your final answer. Correct. Now moving on to the last question of exercise 7.3 that we have up for discussion. Question number 11. In how many ways can the letters of the word permutations be arranged if the words start with P and end with S, vowels are all together, and there are 4 letters between P and S? So the first part of the question is, first we need to calculate how many letters are there in the word permutation. So we have 12 letters, and the only letter that is repeating is that we have 2 T's that are repeating, right? So for the first part, we have P in the beginning, 10 letters here, and S at the end. We need to calculate how many ways we can permute when P and S are starting and ending letters, right? So we have 10 letters. Of these 10 letters, only T is repeating, and T is repeating twice. So 10 factorial upon 2 factorial, and that is nothing but 10 factorial divided by 2, and that is nothing but 181 440. Correct. And that is your answer. These are the number of different permutations that are possible when the word starts with P and ends with S. Correct. Moving on to the second part. All the vowels in the word are together. Right. So the thing that we did in Mississippi, we consider all the I's as a single letter. We're going to do the same thing in permutations as well. So the vowels that we have is we have one E, we have one U, we have A, we have I, we have O, and we have all the vowels in the word. So we have 5 vowels, and the total number of letters that we had in the word are 12. So consider these 5 as a single letter. So what you now have is 7. So you have 12 minus 5 plus 1 letter, number of letters, because these 5 are to be considered as one letter. So the total number of letters that we now have are 8. Correct. But before actually finding out the answer, one thing that we need to keep in our minds is that you can also permute these 5 letters amongst themselves, right? So the final answer that we are going to now get is going to be 8 letters permuted upon the repeating number of letters in the frequency. So we have again 2 T's that are repeating, so we divide that by 2 factorial into 5 factorial, because we need to make sure that we understand that these 5 vowels can also be permuted amongst themselves, right? So the final answer that you're left with is 8 factorial upon 2 factorial into 5 factorial, and that is nothing but 20610 into 120, and that is in fact nothing but 2419 2419200, right? So that is your final answer, and that is how the second part of the question is solved. Correct. Moving on to the last part of the question and of the exercise. We need to calculate the number of ways letters of permutation can be arranged if there are always 4 letters between P and S, right? So imagine this: 1, 2, 3, 4, 5, 6, 7, 8. So let me just not, this will be very tedious, right? So there are 12 places that we have to fill, right? For us to permutations, there are 12 distinct places that you have to fill. But suppose you keep P at the first place. P is and S. I'll just write their positions. So if P is at the first place, then the position of S is fixed. It is at the 5th place, or not even at the 5th place. 2, 3, 4, 5. So it is at the 6th place. Correct. If this is at the 2nd place, this is at the 7th place. Now, how do I know that? Because it has been already given to us in the question that there are always and always 4 other letters between P and S. So if you go on to enumerate this, right, 5, 6, this will be then 8, 9, 10, 11, and 12. So there are 1, 2, 3, 4, 5, 6, and 7 distinct ways you can fill in P and S to occupy positions such that they have always 4 letters between them. But you could also swap the positions of P and S. right? So 7 into 2 would be the number that you would get for you to fill in the places in permutations with PNS, right? So there are 14 number of ways to fill in PNS with keeping in mind this particular condition, and there are 10 letters left. All that is required now is to permute these 10 letters and multiply the answer by 14, and you'll get the final answer. Correct? So we have answer as nothing but 14. This is the number of ways you can fill in PNS into 10 factorial, because the number of letters and positions that are left is 10, divided by 2 factorial, because you need to keep in mind the repeating t also. Correct? So we have 14 into 10 factorial divided by 2. It is nothing but 1814400, and that is nothing but 25401600. Correct? And that is your final answer. Correct? So this is how you're going to get the final answer yourself. There are other ways of approaching this question as well. For example, the last part in question number 11 could also be done by choosing 4 digits from uh, the remaining letters other than PNS and filling them in the position of PNS. But that would have been more tedious, and this is a very straightforward way of doing things. So it could also be done by combinations, but this is the most ideal way of doing things. So with that, we have completed exercise 7.3 as well. What is remaining now is for us to do exercise 7.4 and the miscellaneous part of this exercise, right? So that is something that is remaining, and we are going to cover that in the coming sessions. But up until then, I would request you all to go on with the solved examples of this chapter, as well as you also need to go with other practice questions that you might be practicing. And that is how you're going to build up the grip on this chapter. And yeah, that is all from my side for this session. And thank you.